Hello, my name is Keith Salazar. I'm a toxicologist working in the New Chemicals Division in the Office of Pollution Prevention and Toxics. Today I'll be discussing how carcinogenicity is assessed in the New Chemicals program as part of the Toxic Substance Control Act, which is better known as TSCA. The views presented today are my own and do not represent agency views or policies. So first, I'd like to give a brief overview of TSCA. It was enacted in 1976. It was most recently amended in 2016. I will only be speaking to how new chemicals are assessed under TSCA in this presentation. The New Chemicals program has historically served as the gatekeeper by conducting screening level assessments for chemicals before they enter the marketplace. The New Chemicals program is run primarily out of the New Chemicals Division, better known as NCD. Any substance not on the TSCA inventory is considered new in the eyes of the law, and the inventory currently contains over 86,000 chemicals. What makes conducting risk assessments particularly challenging in the New Chemicals program? The speed at which they must be completed and the lack of any data requirements. Depending on the type of submission, EPA has either 30 or 90 days to complete both the risk assessment and risk management review. Real-world implication of these deadlines means that a toxicologist in New Chemicals has on the order of hours or a few days at most to make a decision on how to assess a chemical. And this is often done without any human health data. Another challenging aspect of conducting risk assessments in new chemicals is the high volume of chemicals that are submitted each year. We average around 400 to 500 per year, and a staff of around 10 human health toxicologists to do that work. So how do we in NCD develop assessments under these constraints? Well, we start by building a weight of evidence with the information that we do have. Our assessments are based on physical-chemical properties that are either measured or estimated by our in-house chemists. The PChem properties serve as the basis for estimating absorption. We'll also consider steric hindrance of certain reactive groups and how they may impact the toxicity. To evaluate cancer, we always run 3 in silico models for every chemical we see. Those tools are Oncologic, the OECD QSAR Toolbox, and Derek Nexus. Finally, we conduct an analog search to identify chemicals with data to inform that. So Oncologic, in case you're not already aware, is a tool to predict carcinogenic potential that was developed by EPA. It outputs 6 possible results on a scale of ranging from a scale of low to high. Any results other than low will trigger an examination into the plausibility of the cancer hazard. This examination is most often resolved by then identifying analog data that may inform the mechanism and plausibility of the genotoxicity and carcinogenicity potential of the new chemical substance. The most common oncologic result for a new chemical substance is low moderate. We consider the toxicity of not only the new chemical substance, but also the potential hydrolysis or degradation products that could form at any point in a chemical's life cycle. We evaluate 3 populations and their associated routes of exposure. So for workers, we're evaluating inhalation and dermal exposures. For the general population, we evaluate releases to drinking water and air releases that may occur as part of the manufacturing process. For consumer uses, we'll evaluate dermal and inhalation exposures that could result from use of the product in the final formulation. So now that I've given you a brief overview of our process and our legal obligations, I'm going to walk you through a couple of real-world examples that we encountered in our reviews. So for the first example, we received this substance as a new chemical submission. It's publicly available. It's 3-methyl-2-butanoyl chloride. There are no human health data of any kind for this substance that we could find. Our chemists expected that the substance would rapidly react in water to yield hydrochloric acid and 3-methylbutyric acid. Oncologic yielded a low moderate concern for cancer based on the chemical class of acyl halides. And this low moderate concern was restricted to the inhalation and oral routes. The Nexus applications, Derek and Sarah, both had equivocal calls both had equivocal to negative predictions regarding the mutagenicity of the substance. So this low moderate cancer concern triggered then a deeper investigation into the plausibility of the chemical's carcinogenic potential. We identified several analogs that are confidential structures that cannot be shared, but the data in every gene tox test we could find was negative. In addition, we reviewed the OECD SIDS for acid chlorides, which did not identify genetic toxicity or carcinogenicity hazard for any of the chemicals in that class. Therefore, we ultimately concluded that we did not assess this substance as a potential carcinogen. In the second example, we received a new chemical submission for a chemical that was analogous to pigment yellow 83. Yellow 83 was a good analog for a number of reasons, which includes that it had similar in silico results regarding the genotoxicity and carcinogenicity. Pigment yellow 83 was identified by Oncologic as presenting a low moderate concern for cancer based on aromatic amines. Derek concluded that it was a plausible carcinogen based on polyhalogenated biphenyls. Sarah had a negative prediction for in vitro mutagenicity. When we looked for available test data on pigment yellow 83, we found that there were two-year bioassays in rats and mice, which did not observe an increase in tumors. In addition, we also found that yellow 83 is negative in 2 tests. Finally, we also reviewed other agency conclusions for these class of compounds and found that the Australian New Chemical Program, better known as MCMAS, and OECD SIDS both concluded that these class of compounds were not carcinogenic. So altogether, considering all this evidence, we ended up concluding that the new chemical substance was not likely to be carcinogenic. Now that you've seen what kind of scenarios we encounter and how we arrive at our decisions, I'd like to reiterate some of the challenges that we have for our program. So as I previously said, there's no data requirements for any new chemical submission under TSCA. We must determine both the hazard and risk for every new chemical submission with scientifically defensible methods. And cancer in particular is one of the highest priority endpoints. One particular challenge with using in silico models is that sometimes it's difficult to ascertain what data or data set is the basis for the alert that's being fired. This makes it very hard to verify if the alert makes sense for our particular new chemical substance. So sometimes we may identify data which contradict the alerts for a number of reasons, some of which may be due to the fact that the data is confidential. And when the mechanism of the cancer alert is not well defined, this also puts us in a difficult position evaluating the data that we do have. So during our discussions with a chemical company, we may be asked what EPA's testing recommendation would be to clarify a potential cancer concern. And without a firm grasp of the mechanism, it puts us in an awkward position of not knowing what data to ask for. I'll say that in my time with the agency, we've never received a 2-year bioassay, so they're basically just not ever done for our program. And our most common data that we do receive to inform carcinogenicity and genotoxicity hazards are the OECD in vitro gene tox tests that are Since we are so data poor, we often make conservative assumptions regarding the ability of a chemical to be absorbed and metabolized once it enters the body. The new chemicals that we review are often a combination of smaller, well-studied chemicals. Common question we'll ask ourselves is how bioavailable is the particular carcinogenic moiety. The tools that we do have, such as the OECD QSAR toolbox, while they do provide potential metabolites, it doesn't indicate how likely it is to form. That being said, this is an active area of research within EPA and our sister offices, the Office of Research and Development. So, although I've shown you examples where we were able to dismiss the cancer plausibility, we often have situations where we cannot dismiss the cancer alert. Since we must quantify the risks associated with any hazard, we'll search for any available slope factor RUR for an analog that makes sense. But more often, we end up using a slope factor derived from the very small moiety that is firing the alert. So in the case of yellow dye, we might have used something like methylene dianiline or PCB to quantify the risks if we did not have strong evidence that the substance was not a carcinogen. We are currently working on using other tools like generalized reacross, also known as GENRA, to help better understand the confidence response. So we and others are moving forward on NAM-informed strategies to address some of these problems that I've described. We're actively working with our colleagues in ORD to address these data and methodological gaps, developing case studies that apply GENRA or other open source QSAR could improve the effectiveness of carcinogenicity gene tox space. There are also other new technologies that could help provide insights on human relevance, such as Tox Tracker for gene tox endpoints. Assessing transcriptomic markers could be a part of a broader profiling to understand the point of departure. Finally, there's promising new work mapping tox test endpoints to key characteristics of carcinogens to help develop QSAR models to predict chemicals that act across a network of events relevant to carcinogenic outcomes. The new chemicals program is excited about the roles of NAMs as a tool to improve hazard and risk assessments in our data poor environment. As you are all aware, cancer is a complicated endpoint, so multiple in silico and in vitro approaches will likely have to be used in tandem in the future. With that, if you have any questions or comments, that the following address. Thank you very much for your attention.